Welcome to our video supplement here on optimization. We are going to look at two problems. Perhaps you want to hit pause and try them before we proceed. The first problem details a situation with the ellipse we have the equation of on the screen. Remember, since the denominator with the x is larger than the denominator with the y, we know that this is going to be a horizontal ellipse. We can draw in the horizontal ellipse on our screen. But the other thing to be careful of when we're dealing with optimization is think about what really matters. If we optimize the rectangle inside of the ellipse whose equation is provided, and we just move that ellipse around, it should not affect, and it will not affect, the rectangle of maximal area. So rather than dealing with the equation that we have, let's shift it so that the ellipse is centered at the origin. It's easier to work with, and it will lead us to the same answer as if we had done it with the original equation. So once we have rewritten that equation, we're going to consider our ellipse as being centered at the origin. That means this point up here will be up 2 from the origin at 0, 2. This other point will be down 2 at 0, negative 2. Over here, we will be at 5, 0 because of the denominator of 25. And over here, we're at negative 5, comma 0. Remember how ellipses work. Now, really what we care about is having this rectangle be drawn in. And when we draw in the rectangle, we like to draw it so we're not assuming anything about symmetry or such. So there's going to be a rectangle. We want to maximize the area of that rectangle. Now this point here is going to be at a point x comma y that satisfies the equation we have. Also notice that if we were to draw in a set of axes, and we'll just freehand them for a second, then this dimension right here is our x, and really the full length of the rectangle is 2x. And this dimension of our rectangle is y. The full dimension would be 2y. So when we go to do this, the first thing we're going to do is get y by itself in this equation. We'll have y squared over 4 equals 1 minus x squared over 25. Y squared is equal to 4 times the quantity 1 minus x squared over 25. Take the square root on both sides with that equation. Square root here, and we get that y is equal to 2 times the square root of 1 minus x squared over 25. Now what we're trying to maximize or minimize is always the equation that we want to focus on. Here we're trying to find the maximum area, so we want to really focus on the area equation. And the area of our full rectangle, as we've discussed already, would be 2x, which is really like the length of the base, times 2y, which is truly the height. So the area is going to be 4xy. Now the key thing is we just want this equation in terms of x, so we can plug it into our calculator. In other words, we're going to take this expression for y and substitute. So it'll be 4x times the quantity 2 radical 1 minus x squared over 25. That's what we will go to our calculator and put in the y equals. Now please, when we do this, don't try to simplify too much before we go to the calculator. It's just easy to make a mistake if you try to simplify significantly by hand. So we're typing this in, 4x times 2 square root 1 minus x squared divided by 25. Make sure to close our square root. Make sure to double check that we don't have any typos. When we go to the window, x is how far from the origin we are. It can't be any larger than 5. Look at our picture. So when we set up our window, we want to do so intelligently. 0 to 5 would make sense for the x. The y would be the area. Let's say that x was 5. We're not going to have an area of more than, say, 100. So let's make the y min 0, y max 100. Now we can kind of play around with the window a little bit, but we'll hit graph. And we don't need to play around a whole lot. We can just go ahead and trace to calculate the maximum point, which is option 4. Will be on the left. We'll scroll to the right, or we could just type in a value for the right bound. We can take a guess. I'll just type in a value, and then we will get the actual maximum value. So in this case, we see that our maximum value occurs when x is equal to 3.536. Please, at least 3 decimal places. That gets us prepared for the AP Calculus exam senior year. 3.536. However, we wanted the dimensions. We wanted the dimensions of the rectangle of maximum area. So we have to do a little bit more here. Remember, one of the dimensions was 2x. So we can just go back to the home screen on our calculator. If we hit x, it keeps the full decimal. We want 2x, which is 7.071. Now keep in mind there were not any labels on this, so we'll just leave it like that. By, we need to know the other dimension. And to get the other dimension, we will plug in to the expression that we had for y. So we're going to come over here and we'll take 2 times the square root of 1 minus x squared divided by 25. Now that's our value of y, but we need to double it because the overall height of our rectangle was 2 of those y's. So 2.828 would be our other dimension. We will come down here, 2.828, and there's our final answer. Now we will contemplate one more problem. The problem is pictured on the screen. Perhaps you want to hit pause before we begin. Okay, so first thing is we're trying to minimize the surface area of a can, and we've got a can, so we'll just draw some kind of a cylindrical can on our screen here. With the can, we're trying to minimize the surface area, so we would like an equation for the surface area. Now, surface area of our can contains both the top and the bottom, which are 2 circles, each of which would have an area of pi r squared, where r is the radius. Plus, we would have the wraparound portion of the surface area, which is the circumference of our circle, 2 pi r, times the height of the can that we will call h. This is the formula that we're trying to minimize. So ideally, we would like to get rid of the h and have that formula entirely in terms of r. To make that happen, let's go back and look at the fact that our volume is 850 milliliters. Volume is the area of the base times the height. So in this problem, 850 would be equal to pi r squared times the height. And if we want to get the h by itself, we just divide both sides by pi r squared. We will now take this expression and we'll plug it in for the surface area. So surface area is 2 pi r squared plus 2 pi r times 850 divided by pi r squared. Now notice our surface area formula is just in terms of r. We can now turn to our calculator, put that in for our equation, graph it, and hopefully identify the minimum. So we will go ahead and type it in. 2 pi times, now we have to use x instead of r, x squared, plus 2 pi times r times 850 divided by, now put parentheses around the denominator, pi r squared. Make sure you put the parentheses around the denominator though of pi r squared, otherwise you're not going to be graphing the correct item. We'll turn to our window, and maybe we just want to go 0 to 20 for the x, maybe we want to go 0, 1,000 for the y. The y is the surface area, the x is the radius. This might not be a good graph, but you just kind of go with the flow and adjust as needed. We do see a nice picture. We will calculate the minimum. We'll go to the left, we'll go to the right, we'll take a guess, and we get an answer. So the answer we get says that x is going to be equal to 5.133. Please, at least 3 decimal places correctly rounded. But that's not what we want necessarily. Keep in mind that that's our radius. 5.133. Now for a unit, this problem was talking about milliliters. Milliliters correspond to centimeters. A cubic centimeter is a millimeter. Cubic centimeter is a milliliter. And now we need to find the height of the can. To get the height of the can, we're just going to plug it in to the h expression we found, which was 850 divided by pi r squared. So we get our calculator back, we go to the home screen, we type our x, make sure we have it. We type 850 divided by the quantity, pi x squared. Hit enter, and we're getting 10.267. So the height is 10.267, and that would also be centimeters. That would be the set of dimensions of the can having minimal surface area. So again, what you want to do is determine which equation you're maximizing or minimizing, in other words, optimizing. You try to get all of the variables in terms of just one variable. So in this case, we found the height in terms of the radius, converted everything into a radius, went to our graph, identified the optimal point, and then answered the question. Really, that's all there is to optimization, although sometimes setting up your equations and getting them in terms of a single variable can be difficult.